In part 2 of the Module 5 lecture on clustering, we'll be talking about k-means clustering. Recalling from last time, we introduced the concept of hierarchical clustering and two methods therein. Then we discussed representations, how to represent a particular cluster of multiple points using single summary points such as clustroids and centroids. Following that, we talked about methods for calculating distances between clusters, and then stopping conditions to identify when we should stop clustering, or identifying how many clusters we should have in our data. When we discussed clustering, we talked about this in loose terms as identifying groups in our data where points in the same group should be similar in some way, where we've defined similar or hope that similar has some real-world meaning. We also provided a formal definition of clustering, where given some set of points in some space, and a distance metric between them, or between points, that allows us to evaluate or quantify how similar or dissimilar two points are in this space. And the objective of this clustering task is to group these points into k clusters, where you either specified k beforehand, or we've performed some optimization to allow k to be extracted from the data. This objective has got two constraints. The first is that points in the same cluster ought to be similar to each other, or close to each other given our distance metric, and points in different clusters should be dissimilar from each other. We talked about how clustering in two-dimensional space, with these low-dimensional spaces, is a relatively straightforward process. But this becomes complicated or more complex when we start talking about higher dimensional spaces that you might find in general real-world data sets, such as text data, where you have dimensions for different words, image data, where you have dimensions for different pixels, other kinds of spaces where you have hundreds to thousands of dimensions. So how do we cluster in this space? As I mentioned, we talked about hierarchical clustering. Specifically, we talked about two methods: agglomerative clustering, where we start off where all points exist in their own clusters, and then we iteratively combine clusters until we have a full clustering across the data. We generate this hierarchical structure, or dendrogram, from the bottom up. Conversely, we also have the top-down method, where we start with a single cluster and recursively split it out until we have some target number of clusters in our data. Finally, we have a separate method called point assignment clustering, where we maintain some set of clusters and we assign points to those clusters based on what cluster a point is nearest to. So given some set of points here that drop into or appear to be three different clusters, we would identify these three spaces and be able to assign points to them as new points come into the space or we get new points in the data. When we talk about k-means today, k-means is a very clear example of a point assignment method. We also discussed ways to represent clusters or aggregations of points. Specifically, what we want to do is represent the location of a given cluster, where this location represents or somehow captures a lot of information about all the points in that cluster. So here we want to answer the question, what is the position of this cluster? In the Euclidean case, the first case that we introduced, we talked about cluster centroids, where we just take the average of all points in the cluster to create a centroid at the center of this cluster. And the centroid may or may not be a point actually from our data set. We can contrast this with the non-Euclidean case, where we can no longer talk about averages of points, and instead locations can only be referred to by the points themselves. Given this case, like I said, we can no longer talk about averages, so we introduce a different representation here called the clustroid, where the clustroid is defined as the point that's closest to all other points in a particular cluster. So in this visualization at the bottom, you have three data points in this cluster. We have the centroid, which is not one of these points in this cluster, might be defined as the mean or the average point across these 3 points. And then we have the clustroid, which is a specific data point from this set that is closest to all other points. Now, from statistics, you may equate this to a mean or an average versus a median or mode, where the average doesn't necessarily represent a value from your data, and the median is explicitly taken from the data. You can think of this in a similar kind of way. Then we talked about methods for calculating distances between clusters. We talked about two approaches. One is just comparing distances between these cluster centroids or clustroids. So we take these centroids as essentially a summary statistic for all the elements in that cluster, and then you can compare or treat these clusters as essentially points in space, and then evaluate distance between them as though they were points rather than aggregations of points. Alternatively, you can introduce additional metrics like intercluster distance that you want to try and minimize. And then finally, we talked about stopping conditions for clustering. Now, for agglomerative clustering or divisive clustering in this hierarchical case, really what we're trying to do is identify when we should stop breaking down clusters or stop combining clusters. And maybe we know or can identify this through domain knowledge. So if we are trying to group book genres, we may know the number of genres a priori, just from our knowledge of the domain, and we will stop when we've identified the appropriate number of clusters. And from a hierarchical standpoint, this is a valid representation because you could imagine there's several different types of fiction, from historical fiction to crime dramas, etc. And capturing this from a cluster or from a hierarchical perspective makes sense. Alternatively, you may look at political parties, where even in the United States, you have political parties that are represented by groups of sub-parties. So there's the progressive wing of the Democratic Party and the more moderate wing. There's the back in the early 2010s, there was the Tea Party movement within the Republican Party. So you can again think of this as a hierarchical structure that has two primary clusters, and then these two primary clusters break down. Or you can, again, know from your data, like the quasar versus galaxy case that we talked about, where you have two different kinds of stellar phenomena, and each one of these types, or both of these types, has distinct subtypes, but you know that there's two primary types that you want to look at. Alternatively, you can pick some metric and then stop clustering once you've reached some threshold that you specified for that metric, or you've maximized that metric through some comparison from one iteration to the next, which we've seen before when we talk about Girvan-Newman clustering, where we can iteratively remove edges from a graph, evaluate modularity, our metric of choice here, and identify when that modularity metric is maximized, and that's when we stop breaking up or dividing the data. And when we talked about hierarchical clustering, we briefly alluded to some problems with the implementation for this. At each step, what we have to do is understand or evaluate pairwise distances for all pairs of points in clusters, then we have to merge. From a complexity standpoint, this is problematic. In the naive case, we have order n cubed, and even in careful implementations or highly optimized implementations, we're still talking about order n squared log n. When in previous modules we talked about how n squared is often still too large for the data that we may encounter on the web or web scale data, clearly we need to have some more efficient means for evaluating or building these clusterings. This is still too expensive. So in this week, the second half of Module 5, we'll introduce k-means clustering and how we can use k-means to identify clusters in our data, how we can initialize these clusters. So one of the differences between a hierarchical clustering and k-means clustering is you specify the number of k. Either you've identified a reasonable number from your domain knowledge or from some evaluation of the data through some metric analysis or something, but the clustering generally has some k set of clusters throughout the entire clustering process. And then we will talk about some strategies for selecting this k value. So first, let's talk about defining k-means. In general, we're making some assumption that we're dealing with Euclidean spaces and Euclidean distances. In that space, we then pick some k value that says how many clusters we want to search for or how many clusters we want to create. We initialize these clusters in some way, either picking points from our data or randomly selecting points in this space, and use these points as our centroids for our clusters. And then we want to try and populate these clusters by evaluating or assigning points in our data set to clusters that are close to them. And then we iterate through this process, reevaluating or reassigning points to clusters and updating our clusters until we reach some convergence. So when we talk about these clusters and populating them, what we do is for every point in our data, we want to go and place that point in the cluster whose centroid is closest to that point. So this may be a very intuitive kind of approach where you just look at the different clusters you have, take the next data point you want to look at, and say, of the different clusters, which cluster is this point closest to, and we'll assign that point to that cluster. We'll do this for all points in our data set, and then we look at the resulting clusters and update the locations of our cluster centers. So when we talk about these centroids as being a summary statistic for our clusters, we need to update them based on our new set of assignments, or our new points in space. And then we go back through and reassign all points in the space again based on their closest centroid. So once we've identified the updated centroids, we throw away all of our assignments and reassign all points again by looking at their closest centroid. So it's normal for points to move back and forth or move into different clusters based on this process. And we repeat this process until we reach convergence, where we define convergence as being some stable state in our clustering assignment. That is, from one iteration to the next, points are not moving between clusters, or some threshold number, some small number of points are moving. So you could imagine you've had oscillation where a point moves back and forth between some pair of clusters. So you can set some threshold and say as long as fewer than X points are moving back and forth between clusters, we have reached convergence. So we can show an example here of 11 different points. We'll start off by initializing a cluster using this point in blue and this point in purple as a second cluster. And now we can go through and update all of our cluster assignments by looking at which points are closest to this point in blue and which points are closest to this point in purple. Now, this initial clustering is likely not the optimal clustering, and here you can pretty much imagine that this selection of the X on the far left, this X in magenta, was probably a poorly selected initial point for our clustering. And that's totally fine, because in the next step, we will update our cluster centers, and maybe these are no longer points in our data set, and then we will reevaluate our cluster assignments, and you see things move. And we do this again, re-updating our cluster centers, and again, we reevaluate which cluster centers our points are closest to, and you can imagine this is a stable clustering for these points, and if you were to repeat this clustering process over a few more iterations, these points would not change or move between the cluster assignments that we have. So when we pick points that we'll use as our initial cluster centers, we want to pick these points such that only one point is chosen per cluster. Now this is problematic though, because if we knew how to enforce that constraint, then we would already potentially know what the clustering should be. Because we know if 2 points are in different clusters, that means we have some idea of what the cluster assignments ought to be. So this introduces a question about how do we do this? How do we pick cluster centers, these initial sets of centroids, in a reasonable or intelligent way? That's what we'll talk about now when we talk about initializing clusters for k-means. So the most naive solution, maybe given some points in space, let's just pick k points from our data at random. Where we have specified k as the number of clusters we want. We can pull points at random or extract points at random from our data set and proceed as though those are our cluster centers. Now this is actually a relatively nice kind of approach because statistically when you are pulling random points from your data set, you're likely to hit the more frequent points from your data, which means you're likely to hit the most from the data. But there are downsides to this that we'll get to in a minute, but we can visualize what this looks like. So even if we have a non-optimal initial set of clusters, so say we put these red and green centroids in the top and this blue centroid in the bottom left, when we start assigning points to clusters using these cluster centers, quickly we have a non-optimal set, but then when we update, we can see the cluster centers move, and they move pretty rapidly to the point where we end up with the expected clustering that we would want. We have 3 clearly distinct clusters here. But that's not to say that this naive solution is perfect. There are definitely opportunities for picking randomly selected points that are suboptimal or that result in poor outcomes. So what are the implications of this? What kind of errors may you run into when you've poorly selected your... the first one is slow convergence. So we're talking about having to do multiple iterations for this data, multiple iterations and passes through our data to do the cluster assignments and move our cluster centroids. If you got unlucky and you put all 3 of your points into one cluster, this could be problematic. Also, you could have an issue where the final clustering outcome is suboptimal or represents a poor clustering of your data. So these are certain pathological cases. So imagine you have this construction here where you have essentially a symmetric data set with potentially 2 or 3 clusters here. We'll say 2. So you pick 2 points at random and update your cluster assignments. What you'll see is segmented on a non-optimal axis. And actually, if you run this clustering an infinite number of times, this won't perturb, and you'll end up with what's pretty clearly a poor clustering for this particular data. So an alternative here would be to take all of your points and randomly assign them to different partitions. So you partition the data into k groups, randomly assigning points to these k groups as though you already knew what the clusterings were, and then you identify centroids from those partitions. By using these centers of these random clusters, the idea is you can move away or address this problem of having poorly selected points in your data. There's a problem here. Namely, if you take random subsets of your data, essentially what you're doing is you're sampling your data set. So even if you take k different samples of your data, what is the expected average of a given sample? We would expect the average of a sample to be close to the average of the full data. And what this means is when we take, even if we do 3 different partitions here, the means for all 3 of these different partitions are likely to be close to each other because they're all likely to be approximately close to the global mean of the full data set. So you end up with less variation in the resulting cluster centers than you do with the previous version where you randomly selected points from your data. But like I said, this helps you here because if you take these 9 points and you subdivide them into 2 partitions, you put the initial cluster centers at the centers of those partitions should be close to the global mean, you've essentially addressed this problem. So we saw that how this configuration of points can be problematic in random point assignment, the method that we discussed. Here, this is solved by this partitioning approach that puts your initial cluster centers close to the global mean. But there is a problem here. We can actually see how this problem manifests. So say we have 4 different clusters here. We have selected our k appropriately, and we partition our points into these 4 different partitions: red, green, blue, and orange. So when we extract our initial cluster centers, all of them are going to be approximately in the same place because they'll be close approximations to the global mean for the entire data set. So you have these 4 stars in the middle. A particular issue here, though, is because of the configuration that you've ended up with, where the red, green, and orange stars sort of surround the blue star, when you then update your cluster assignments, no point in your actual data set is close to the blue point or close to the blue cluster center because it's surrounded by these other points. And then you end up dropping the blue cluster altogether because there are no points that are close to it, and you end up with a suboptimal or an incorrect clustering than what you wanted. So we can introduce a better solution here by taking advantage of some intuition. If we think about the clustering process, what would we expect to be the case, or what property would we expect to be true for cluster centers after we have finished clustering? And namely, that is, all k cluster centers are likely to be far from each other. Because remember, in our definition of the clustering task, we want points that are not in the same cluster to be dissimilar, to have high distance, meaning that 2 cluster centers should also have high distance. So we want to pick points that are far from each other. And this is the premise for the k-means plus algorithm. So we start by taking a random point from our data, say this red point in the bottom left, And then when we pick our next point, we pick our next point intelligently such that it is far away. So we can scan through some sample of the points in our data set and identify the point that's furthest away in this sample from our initial point, or the current point, select that one as our next cluster center, and then proceed again, picking a third point that is far away from the previous 2 points. And we can do this for as many iterations as necessary to identify k points, and ideally we'll end up with k points that are at least far from each other. So you end up avoiding the issue of them all being close together around the global mean that we saw in the random partitioning case, and we address issues of 3 points being, or k points being, close together in the same cluster that we saw in the random point selection process at the first one. So we can visualize this pretty easily. So here we have one point that we've selected as our first cluster center. We pick a point that's far away, and we pick another point that's far away, and we see this very quickly converges into the appropriate clustering that we wanted. And even in this pathological case, or this problematic case we saw before, picking 2 points that are far away from each other is an optimal approach or strategy because we end up with the correct kind of clustering, and we do not end up with the case where we have 2 points that were on the same horizontal plane that then lead to the incorrect clustering that we saw. And in fact, there's a website that I can link to here from Neftila Harris, where you can actually visualize this process for point selection. And in fact, how you select points or initialize the k-means algorithm is a whole area of study in and of itself, and there are survey papers on appropriate methods for doing this based on different kinds of constraints and context. So how many points you have, how rapidly you need to identify these centers, and so on. This is a decent paper that summarizes this. Now the last thing we'll talk about are strategies for selecting the number of clusters. So recall from last time, we were looking at the dendrogram. What we want to do is identify when we should stop building up these clusters. When should we stop merging? That's a different kind of task than what we have for k-means. So in k-means, while we also do not know the appropriate value for k, we'll start off with explicitly having set k different clusters, and this is not a merging task. We're trying to continue until we reach some convergence, rather than continuing to merge or divide clusters. So we can see an example of issues that come up when we are trying to pick the appropriate value of k in this point configuration here, where if we start off with too few clusters, then if we're evaluating the within cluster distance for all the points to the cluster centroids, we end up with many points that are very far away from the cluster center. Now again, maybe 2 is the appropriate number you're looking for here, but from this configuration it seems unlikely, where it seems like this data may be better represented by more than 2 clusters. So alternatively, if we get this number correct, then the interpoint distance within these clusters should be, in general, small. As you'd expect in that blue cluster on the left, most of those points are close together. The red cluster on the right, again, most of those points are close together. And we still have the occasional outliers here with the top left point in the red cluster and the top left point in the yellow cluster that are far away from the cluster center. But overall, the average distance from the cluster centers to individual points in the clusters are small. So as we add more clusters to the data, or try and represent this data with more clusters, we'll see that while we are likely to reduce the average distance from cluster center to all points, there's relatively small or relatively little improvement from the 3 cluster configuration before. So if you look in the limit of values of k, once k equals the number of points in your data set, the average distance within clusters is going to be 0. But clearly that's not a useful evaluation. So how do we pick the number of k here? So recall from the hierarchical clustering case, we had 2 methods when we were looking for termination conditions, where we are trying to merge or divide our clusters until we reach some threshold based on the number of k that we've specified beforehand, or through some optimization. So in the case of k-means, we can look at k, we're selecting our k-value via optimization. So when we talked about increasing the number of clusters from 3 to 4 and seeing relatively little change in the average distance to our centroid, we can actually plot this, and we see that as we increase the number of k, we see a rapid decline in average distance to our centroid. But then once we hit some point, then the change in this average distance to the centroid starts to level off. As I said, in the limit, as k approaches the number of points in your data, this value will go to 0, but that's not useful. So we want to identify an appropriate value of k where we have, on average, low distance from the centroid to other points in our data set, but we want to do so without sacrificing a lot of complexity or having to go through many more passes in the data and adding more clusters to the data. And in fact, this general kind of approach where we look for this point of diminishing returns is often referred to as the elbow method, where you look for values of k where some particular metric of interest for you or quality metric of your clustering no longer improves rapidly. Now there's a third option for evaluating k, and again this depends on your task, but we've been talking about clustering in terms of characterizing clusters in our data. So we want to be able to look at data and points in our data, see what the clusters are, the general structure of this data is, because we expect these clusters to tell us something about the data. Maybe this is a dimensionality reduction case because you want to reduce the amount of data you have from your full feature set to just a variation across the different clusters that you've identified, or you're trying to do something else that is focused on understanding what the clusters mean. But that's not actually entirely necessary, because what you could be doing instead is using these clusters in some sort of downstream task. So for instance, if you're trying to use clustering for dimensionality reduction, maybe you don't know what the lower dimensions represent. You don't know what individual clusters represent, but you want to use this lower dimensionality space for some other sort of classification task for machine learning, or maybe you're trying to do compression or something along those lines. You don't actually care about what the clusters represent. You just want to use the cluster assignment information in some downstream task. So then you can optimize or select a k value that fits or results in the highest performance of your downstream task. Maybe you're looking at accuracy or F1 or precision and recall for some classification task, or correlation like Pearson's coefficient, or mean squared error if you're doing some regression. So that's a third option, but again, it depends on what you are trying to do. Now you may ask, what is the difference between this elbow method that we just introduced and stopping conditions, the termination conditions we introduced in the lecture last time for hierarchical clustering? And really it's about conceptualizing what the k value means in these two spaces. So here in the hierarchical clustering case, the k value that we're trying to identify, or the metric we're trying to optimize for, tells us when we should stop merging. So specifically in the agglomerative case, where we start with n different clusters and we're going to cluster up or merge clusters up the dendrogram, there is at some point where we no longer are getting a lot of useful information and our merging should stop. In contrast, with k-means, there's no merging, and we're not trying to identify some point where we should stop merging or dividing clusters. Instead, we assume that there is always some set of k clusters in our data set, and the question is about assigning points to those k clusters. And we'll only stop after convergence, so how we use the k value in these two cases is going to differ. So how we might try and optimize or identify the k values will also differ. So that closes out our discussion of clustering, where we've introduced k-means clustering, how this process identifies clusters. We've talked about initializing clusters in k-means, and we've talked about strategies for selecting the number of clusters and what that means for k-means versus hierarchical clustering. So the book introduces some optimizations for k-means to make k-means faster or deal with data that can't fit in memory. And there are many such optimizations, and there are actually a number of different versions of k-means and a number of other clustering algorithms that exist that I mentioned at the end of discussion last time. So I encourage you, if you're interested in this topic, to check those out. If you have any questions about clustering or anything that we've discussed, feel free to post in the discussion forum for